you this thermo-PW code that is a Fortran driver for Quantum ESPRESSO routine, and it is something that I developed in the last 2 or 3 years. So what is thermo-PW? Why I decided to implement it? And so it has 3 parts, and I want to show you these 3 parts. Well, first of all, it is an asynchronous driver of the PW and phonon direct routines, and it started as an asynchronous driver for the phonon, basically. But with time, it became also so I continued adding parts. So there are now in this thermo-PW also some pre-processing tools that I think are interesting, and I want to tell you about their existence. And there are a set of post-processing tools that also I think could be interesting. So, first of all, what it is? Well, it is a Fortran driver that allows the simplification of calculation of selected material properties. So it is less flexible than PW or the phonon, but if you want to calculate the material property that it is able to calculate, well, it requires less information from the user, and it allows you to obtain directly the result without having to set up complex workflows. So it is a Fortran driver for pH and PW, and for any other Quantum ESPRESSO routine. Basically, it is written in Fortran, and so it uses the image parallelization of all the Quantum ESPRESSO machinery, and it allows to send in parallel several PW or several pH. But what is more, also Quantum ESPRESSO has this possibility to send different images. We have seen this morning that there is this feature. What is interesting, I think, in thermo-PW is that if you send the images in Quantum ESPRESSO, you have to know at the beginning, before sending the images, which image does which work is given to which image. So images do not talk among themselves anymore, and you must know from the beginning how much time each task takes. And if you run PW or pH, this is not very easy to do. So it depends on how fast is the self-consistency. It depends on type of Q point, type of irreducible representation. And what the thermo-PW can do is to send these images in an asynchronous way. So you can, when an image has finished its task, it can communicate to a master image that it can do other work, and the master image can give the work at runtime. So at runtime, you have the distribution of the workload. So even if you do not know from at the beginning how much time each task will take, the code will run in any case, and hopefully can distribute the workload better. But then there are a set of pre-processing tools that reduce the number of information that can be provided that must be provided by the user. We have seen this morning that now there are several tentatives to do this kind of thing with tool code, with helper codes, but you have to synchronize all this work. Instead, in a Fortran code, at least for the property that it calculates, you don't need to search around for these helper tools. And then it can produce the quantity, the plots of the quantity that you want to do directly, so without having to go to the codes that are in the post-processing directory, and simply you have immediately the result. And this might be an advantage if you want to do a lot of codes, a lot of materials, where you have just to send this code, or in any case, much less code than you have to send in Quantum ESPRESSO. So why to set up a new workflow? Well, basically because with many CPU on parallel machine, if you don't want to go in the direction of just increasing the size of the system to exploit the power of this parallel machine, another possibility is that you send many copies of PW, many copies of the phonon, and you do simultaneously a lot of calculation dividing into images the number of CPU. And so a typical example of this that was the original motivation for ThermoPW and for its name was the calculation of thermodynamical properties. In the calculation of thermodynamical properties, you have to send many phonon calculations for many different geometries. And you might, if you have a lot of CPU, you might want to do this simultaneously, sending to different groups of CPU different run. Another example might be frequency-dependent calculation. I put here the dielectric constant. If you use some method that does one frequency after the other, now you have to send many times pH. Instead, with a driver like this, all these frequency can be parallelized. And so ThermoPW is made to drive this kind of calculation and to go into this direction. So how it started? Well, we started from the idea of using grid and images in the phonon code. You know the phonon code has G-vector parallelization, bands, task groups also, and the K-points. But the phonon has other two levels of parallelization that we wanted to exploit. And a few years ago, we started to think how we could exploit this level of parallelization. One is a parallelization over the Q vector, and the other is parallelization over the irreducible representation. And the first idea that we got was to use the grid approach. In the grid approach, basically, what one does is that you put in the input the Q vector that you want to do, the irreducible representation that you want to do, and you have to set up some scripting machinery that collects all the results, keep track of where the files are, collects the result. A difficult task for somebody that starts using the code and have to learn a lot of subtle issues on the phone. The other thing that we made after the grid was actually this image feature. So each image sends a Q point or in an irreducible representation. But the problem was that you have to know from the beginning how much time a given Q or in the given representation will take. If you don't know this, the load balancing among images is difficult. And moreover, also with this approach, even now in the image feature of pH, you have to run pH another time at the end of the calculation to collect all the results. And ThermoPW has a master-slave approach that solved these kind of things. Images communicate to the master after they finish their calculation that they are ready to do another calculation. And the only thing that all the images have to know is which kind of work there are. And they communicate just that they have finished their work, and the master communicates the number of the work that it has to do, so the K point and the reducible representation. And all this is done via MPA call. But then, after doing this, we have seen that it was not useful to limit this kind of approach just to the phonon code. We could add calls to PW before the phonon. So doing a complete phonon calculation with bands, self-consistent calculation, bands, and then phonon. And we could do this for several different geometries. So at the end, we could collect all the results and compute anharmonic properties. So this is for the part that regards thermo-PW. And now let me tell you a few words about what it can do as a pre-processing tool. Well, first of all, something that was not contained in Quantum ESPRESSO and that I think is interesting, there is now a tool to recognize the space group. So it can recognize the space group.
It is not included directly in Quantum ESPRESSO. What's the need of including it in etc.?
Well, first of all, because it had to work. So it was not very easy to do, and we started...
Quantum ESPRESSO does not work?
No. I mean that Quantum ESPRESSO is well tested. This thing was not yet very well tested, so we started to put it here.
It has to be moved.
No, it can be moved if we find that it is very interesting and all the others find it useful. Yes, why not? It can be moved in Quantum ESPRESSO.
So this is the opposite of what is already present, that if you provide the space group and you get the structure.
Yes, what is now implemented in Quantum ESPRESSO is that you give the position of inequivalent atom and the number of the space group, and you get the structure. But if you no, this is included. What is here is instead a machine that recognizes the space group. So if you don't tell it to thermo-PW, which is the space group of the geometry that you put, it recognizes the space group. But then the thing that could be useful is, on one thing, this new proposal of k-point path that depend on the on the space group. So it could be used for that. But the other thing that I think could be used, but even this disrupted all that was already well tested in Quantum ESPRESSO. Several runs that were well tested in Quantum ESPRESSO. If you put this second thing, that is to select the factors of the FFT grid on the basis of the space group, what happens is that in this way you include the fractionary translation in those cases in which the FFT mesh is not compatible with the symmetry. And for this, it is useful to know which are the fractionary translation in each space group, and so you can try to optimize the FFT mesh. It's not yet perfect, but I think it is something that is useful.
Actually, I think this is the fact that fractional translations have to be commensurate to FFT is accidental. I mean, if charge densities were symmetrized in reciprocal space, there's they are actually
the phonon is not yet this.
It's not convenient. It's possible. It's not convenient. In phonon, I don't know how it can be done. So it works, but not for all cases. That's the problem.
So this is yes, the feature that is not yet clear if to keep the old FFT mesh. So it is something that we will see. Then there is the automatic generation of the path for band structure and phonon dispersion. That is something that I think is useful. You can produce directly the band structure plot without having to study the form of the Brillouin zone, the coordinate of the k-point, or using some tool codes that gives you the k-point of a path. Another interesting feature, I think, is this, the automatic reorientation of the Bravais lattice, something that is not yet perfect, but on which I'm working. I like that it works well. So at the moment, Quantum ESPRESSO searches the symmetry only among a given set of symmetry. And if you give with the Brav equals 0 the direction of the z-axis, for instance, of an hexagonal crystal that is not along z, you might lose some symmetries. So an interesting possibility is that Quantum ESPRESSO rotates the Bravais lattice in the direction that he wants to have a symmetry compatible with the direction of the Bravais lattice. And then automatic generation of strained lattice for elastic constant calculation available for some lattices. For post-processing, one thing that I'm particularly happy is this. The symmetry analysis of the bands was limited so far to points within the Brillouin zone, so inside the Brillouin zone, that are the white parts of this path. So in this path, you can use the irreducible representation of the point group to find the symmetry analysis of the bands. But at zone border and with non-symmetric space group, this is the example of silicon that is non-symmetric, there are points at the edge of the Brillouin zone, the one that here are written in, where the point group is written in orange, or the paths that are in yellow or in pink, where the irreducible representation of the point group are not enough to classify the bands. In the gray area, instead, are regions in the border of the Brillouin zone where, however, the fractional translation are such that you can use the standard symmetry. Finally, there is the possibility to and I want to say that there is a poster at the Total Energy on this that if you are interested, I will be happy to talk to you. There is the possibility now to plot the band structure of surfaces and the projected band structure and the identification of the surface state on surfaces. And then instead the part of the post-processing tool that we are interested at the beginning, the calculation of anharmonic properties, such as the volume as a function of temperature of silicon. Here, there is a poster at Total Energy of Mauro Palumbo on this issue for HCP crystals. And finally, a few considerations on what to do next. Well, I have to say that the experience of doing thermo-PW has been very positive. And I have, so there are a very high number of downloads. So I don't know if it is because the download machinery is not very, I mean, it gives very high numbers, but if somebody continuously download, so has some script that downloads the code.
It's much more realistic since August, when we realized that most of the downloads were fake and coming from a few Chinese IPs. Now it's much more realistic.
In any case, I received some interesting user comments on this and suggestions for implementation of new feature. But I have to say that thermo-PW has been an experiment so far. So it is not yet a production tool. You do not have to expect that it is as solid as Quantum ESPRESSO. There are some features that are still incomplete or work only for a few crystal systems. And so I think that, this project is very, very useful. I want to continue it. And, but I think that in the next years, it has to be refined, cleaned, and all the features that are already there completed. That's it.